Hi everyone, I'm Seungbae. Thank you for joining our tutorial, Fairness in Computer Vision, Datasets, Algorithms, and Implications. This tutorial is organized by Angelina, myself, Professor Olga, and Professor Jeong-seok. We are very excited to have this tutorial on fairness in computer vision. This tutorial introduces recent ideas in computer vision fairness and shares pointers to some important literature. Our target audiences are researchers and practitioners who want to use computer vision tools even without having technical backgrounds. Advances in computer vision increase the utility in a wide variety of applications. For example, object detection is used in driving automation by recognizing nearby cars or pedestrians. And face recognition is used to detect and analyze face attributes, emotions, or even personalities. In addition, image captioning is used to explain images by generating text descriptions based on detecting objects and understanding the relationship between the objects. As the computer vision technologies are used in such tasks, it is imperative to consider fairness in computer vision. The computer vision community has taken fairness concerns very seriously. In the recent literature, there has been an increasing amount of work on quantifying and measuring fairness, bias measurement and mitigation, accuracy gap reduction, and developing new resources for improving fairness in computer vision models and datasets. The tutorial has two main parts. The first part will focus on understanding biases in computer vision. I will cover where the computer vision biases originate from and what their impacts on our society. Then I will review three types of biases and mitigation strategies widely used in computer vision with key reference papers. In the second part, Angelina will present how to apply computer vision with fairness consideration with a running example. Let's take an automated recruitment as an example of a practical application that uses computer vision models. With the advancement of machine learning technologies, more and more companies are using and applying automated technologies to the hiring process. Automated models can analyze and evaluate applicants' resumes and match them to the right department and generate interview questions to evaluate the applicant's abilities or help with the scheduling throughout the recruitment process to hire the suitable candidates. An automated video interview can be an example of a practical computer vision application. Automated video interviews are conducted based on computer vision technologies to assess candidates' soft skills, motivation, proficiency, and expertise by using face recognition. This automated tool might help companies objectively evaluate the candidate. However, what happens if the pre-trained computer vision model is used in this application is biased? What if the pre-trained models favored males over females because of a skewed training dataset? If the model is biased, then the automated interview tool may produce an incorrect assessment or unfair treatment across different genders or race groups. This can be a big social problem, such as discrimination against a particular gender or race. Then where do these biases come from? Bias can be created in many places, but we can consider it from two perspectives: social bias and media bias. Social bias is the result of stereotypes or psychological cognitive bias commonly held by the individuals or societies. The recent study shows that there is a clear difference in people's perceived emotions according to the genders. For example, people tend to perceive female faces as happier than male faces. If people with these stereotypes label the dataset, then they will create a biased dataset. Media also plays a big role in creating visual bias. There are many reasons, but depending on the media, it is possible to provide biased images only to a certain groups. Conservative media, for example, can often offer good-looking pictures of conservative politicians. In addition, images containing a specific group may have distinct characteristics compared to the other groups. For example, photos related to sports may have more males than females. And the recent study found that the images of conservative politicians contain more objects such as flags and uniforms, but the images of liberal politicians project an image of care of the community. Data bias can happen if a data set is built with the only photos provided by a specific media. And besides the dataset bias caused by the social and media biases, biases can be amplified in models. These two graphs show the relationship between dataset bias and model bias in two popular datasets. The x-axis represents the gender bias present in the dataset, and y-axis represents the gender bias in the prediction result of the model trained with the biased dataset. As shown in the graph on the left, shopping and cooking were more biased towards females, and the bias towards males was amplified for driving. In the graph on the right, spoons and forks produced biased result for women, and sports gear showed result with an amplified bias for men. That is, visual biases can result from dataset bias caused by social and media bias, and model bias can be created by amplifying the bias in the process of learning the biased dataset. So now we know where visual biases originate from. Then what happens if applications use biased computer vision models or datasets? At the user level, it can impact the user's perception by reinforcing the user's prejudice towards biased result. For our society, it can create various social issues since biased result may discriminate against people in certain groups. Then how can you prevent such a harmful impact of visual biases? To prevent having biased results, we first need to understand what types of biases are there and mitigation strategies at different levels. So I will introduce 3 types of biases in computer vision. The first bias is accuracy disparity. This happens when the model's prediction accuracy differs across groups. For example, the model only works well for younger faces, but with poor accuracy on older faces. The second bias is spurious correlation. A spurious correlation refers to a connection between two variables that appears to be causal, but the dependencies between these two variables are due to some unseen information. The third bias is representation in datasets. This happens when each group has a non-uniform sampling size. For example, if 80% of datasets are female and only 20% are male, then there is a representation bias. The accuracy disparity measures the performance gap between the groups of protected attributes, allowing us to evaluate the fairness of computer vision models. Gender shade is one of the most representative paper that cannot be left out of the computer vision fairness. In this paper, the authors showed the accuracy disparity across genders and skin tones in well-known commercial gender classifiers. More specifically, the authors measured the accuracy using the average faces of lighter males, lighter females, darker females, and darker males. The result showed that in all gender classifiers, the accuracy of darker females was significantly lower than that of other faces. In particular, the largest accuracy gap between darker females and lighter males was 34%. A spurious correlation represents a connection between two variables that seems to be causal relationship, but really is not. A causal relationship describes a cause and effect relationship between two variables where one variable directly affects the other. However, in a spurious correlation, a relationship between two variables is due to a third confounding factor that affects both variables. In this paper, Men Also Like Shopping, the authors found spurious correlation in computer vision models. For example, in a given image with a man in the kitchen, the model predicted gender of a person in the image as a woman. We find here a spurious correlation between cooking and gender. In fact, there is no logical causal relationship between cooking and gender, but the reason for this is the result in an unbalanced data set. In the set of images with the label cooking in the data set, there are far more images with the women than images with men. Because of that, if a model sees a spatula or kitchen as a background in the image, it may incorrectly determine the gender of the person in the image as a female. The paper, Turning a Blind Eye, is another representative fairness literature that shows spurious correlation. The authors analyzed the performance of the age classification model using IMDb, a dataset widely used in computer vision. However, in the dataset, they found a significant bias towards younger women and older men. The graph shows that there are more females than male images in ages younger than 30s. And on the other hand, there are many more male images than female images in those in their 30s and or older. In this way, when a model is trained with unbalanced data, a spurious correlation may occur between age and gender, even though there is no causal relationship between these two variables. In other words, the biased model makes incorrect predictions as women are younger and men are older than their actual ages. And this figure shows the feature representation of age classification. However, the features are clearly separable by gender, showing that the model has learned the gender bias in the dataset. The representation bias refers to an unbalanced distribution between groups of protected attributes in a dataset. In the Fairface paper, the authors evaluated benchmark datasets widely used in computer vision. The graph shows that, except for the Fairface dataset, all datasets are severely unbalanced across the race groups. In most datasets, more than half of the faces are white, and they are dominant over other races. The problem is that models models trained on these unbalanced datasets only work well for white faces and can produce erroneous results on images containing faces of other races. Another recent work, understanding and evaluating racial biases in image captioning, the authors showed that gender and races are ununiformly distributed in the COCO dataset. The authors found that there are twice as many males as there are females, and there are 7.5 times more lighter skinned people than darker skinned people in the COCO dataset. They also found that there is a big difference in the object and background in the images depending on the skin tones. For example, lighter skinned people tend to be pictured more with indoor and furniture objects, while darker skinned people tend to be more with outdoor, sports, and vehicle objects. Again, bias in dataset can be learned by models, and that will eventually lead a biased prediction as a result. So far, we have talked about the origins and types of biases in computer vision and their impact on our society. Now I will introduce the types of bias mitigation strategies in computer vision. There are three types of mitigation methods, including making a fairer data set, using synthetic data, and algorithmic intervention. I will go over each strategy and explain in more detail how bias mitigation was achieved. The first strategy to mitigate bias is to build a more fair data set. As we discussed the problem of unbalanced data set, it is very important to have data set where data samples across sensitive attributes are uniformly distributed. For the face data image data set, fair face is known as the first and the fairest data set. The data set has a balanced race composition of 7 race groups, including white, black, Indian, East Asian, Southeast Asian, Middle East, and Latino, as well as a balanced gender composition of male and female. The table shows the gender classification accuracy using different face data sets. The result confirms that the fairer data set helps close the performance gaps over different groups in race and genders. The next mitigation strategy is utilizing synthetic data. For example, the paper gender slopes uses the synthetic face images as shown in the figure. Using this method, the synthesized images that are more feminine or masculine than the original image can be easily generated. This approach can be used to make a balanced data set. For example, we can create more female images if a data set contains a larger number of males than females. On the other hand, synthetic data can also be used for validation purposes. In this paper, the authors generated more feminine and masculine images than original images and used them to assess commercial computer vision tools. Since only the face can be controlled in the synthesized images, it is possible to measure the fairness of commercial tools. Lastly, we can use algorithmic interventions to mitigate biases. Adversarial learning is one of the methods of algorithmic intervention. The goal of adversarial learning is to prevent the model from learning protected attributes. To achieve this goal, regularization loss is often utilized. And this objective function is from the paper Turning a Blind Eye. Here, LP represents the loss of the primary task, and LS indicates the loss of the secondary tasks, which are related to the sensitive attributes. Finally, the confusion loss is added to induce sensitive attributes not to affect the main task. And as shown in these figures, the feature representations were separable by gender in the age classification task before debiasing. However, after using the adversarial learning, the feature representations become invariant to gender. So I introduced some literature to help understand biases in computer vision. And Angelina will continue the second part of the tutorial. Thank you.
Hi, I'm Angelina Wang, and in this half of the talk, I will now discuss how we might apply computer vision in practice and the fairness considerations to keep in mind during this process. The running example we will keep in mind throughout this talk is a scenario where a social scientist wants to filter the contents of a large corpus of archival photographs to study the representation of cars as a method of transportation. In this scenario, it would take the researcher too long to sift through all of the images in the corpus, so they hope to be able to leverage computer vision to filter the corpus to only the images that are relevant to them. To begin with, I will go over how to get started, which entails asking questions such as whether the task is appropriate and finding available tools. When using computer vision, as with all technology and machine learning, it is important to consider whether this is appropriate for the task at hand. While computer vision technology can be very useful for certain applications in domains like healthcare and accessibility, it has also been used for more concerning purposes, such as in the surveillance of marginalized groups. In one line of work, a comparison has been drawn between the computer vision application of facial recognition to that of plutonium, because of the need to regulate and control facial recognition is argued to be as severe as that of nuclear waste. One of the core problems discussed is that of attributing any kind of numerical value to a face, and the history of such categorization being to grant legitimacy to socially constructed groups such as race. These numerical differences between groups of people have also been used as a legitimizing mechanism for subordination. Relatedly, another body of work critiques the long tradition of the use of computer vision to perform gender recognition. This application has a large set of harms, such as often reifying gender as a binary, and that gender is a trait that can be known from someone's physical appearance or face. These implications harm society at large, but have unique harms for trans, non-binary, and other gender minorities. A newer set of critiques has targeted other kinds of applications of computer vision, still in the realm of facial analysis, along the lines of automated emotion recognition and the care that needs to be applied when considering its various use cases. Now we can apply this question in the context of our running example of a social scientist wanting to filter an image dataset for those with cars. There are no immediate concerns with this task, and since the presence of a car in a photograph is a visually discernible characteristic, we can determine this to be a valid application. So after careful consideration of the use case, it is entirely possible that the conclusion may be that computer vision is not a suitable technology for the task at hand. However, if it is determined that computer vision still makes sense to use for this task, we can proceed to consider whether a model already exists that can be leveraged. One source to look at is a website like one called Papers with Code. This website, as the title suggests, contains a large repository of code bases and models that are associated with various papers, and may already contain a model for the task needed. However, it is likely that a model trained for exactly a particular use case does not exist, and in this case, it is common to rely on a pre-trained computer vision model that can be fine-tuned for a specific task. Generally, pre-trained models come in two types. One has been trained through supervised learning, which means that the model was trained on images and their associated labels. A common pre-trained data set is called ImageNet and involves classifying images into one of 1,000 different objects. Even though this task may be very different from the task a model is desired to be trained for, it helps the model learn important and generalizable features, such as that edges and lines in an image are useful to detect. However, different kinds of biases and associations learned in this data set, for example, that women might appear in the kitchen more than men, might be encoded into these features, although the downstream effects of such associations are still an active area of research. Another type of pre-training is done through unsupervised learning. Here, image datasets without any human annotated labels are used to train a model. Whenever an existing model is used, whether a pre-trained one that will be fine-tuned or a model that already exists and is ready to be used out of the box, it is important to understand how well the model works and any limitations it may have. Model cards have been proposed as a document to accompany released models that explain things like the types of context the model is equipped to handle and any limitations on its application. For example, if it does not work well for certain geographic regions which are underrepresented in the training dataset. Now we can apply this question again to our running example of a social scientist filtering images for those with cars. For this task, we could imagine an object recognition model would be relevant, and these are common and publicly available. However, because we are looking for cars in a very specific type of image, which is a corpus of archival photographs, a generic object recognition model may not be well suited for this task. Thus, it is most likely that while we can use an existing object recognition model as the pre-trained model, we will likely have to fine-tune it on our own dataset. If it is determined that there is no fully existing model that can be used out of the box for one's purpose, then the next step is to acquire a dataset that is suitable either for fine-tuning a model or training from scratch. If one does not already exist, then dataset collection will have to be performed, which is itself a very difficult and nuanced task. We will not go deep into this topic in this talk, but point to calls for evaluating the process of data collection and annotation and turning it into a more deliberate and careful process with institutional frameworks and procedures. Given that at this point we have a model, whether because we downloaded it from online or trained it ourselves, we are now at the stage where we should use existing methods in order to screen for biases in both the data and model. It's important to note that these are not intended to be a set of exhaustive steps to follow, but rather a subset of the fairness considerations that we should keep in mind, and an example of what walking through them might look like. Now I will discuss what kinds of existing methods we should look to in order to screen for biases in the data and model. Overall, it's important to understand the data set our model is trained on, because different kinds of under, over, or harmful representations can impact how a model performs in different settings and have fairness implications. Understanding the types of images in a data set can help to preempt these problems and potentially prompt collecting more images. Luckily, there exists a large number of existing tools and documentations to assist in the understanding of large-scale visual datasets and make this a tractable task. Whether the model has been downloaded from the internet or not, it's important to understand its training data. As an example of why this is important, we consider the geographical distribution of the ImageNet dataset, a common dataset for model pre-training. Most of the images are from the US or Great Britain, with very few from countries in Asia or Africa. Other popular object recognition datasets exhibit similar trends. This can result in models that are unable to recognize common objects in a different kind of context. For example, this shows how soap from Nepal, which is rarely if ever seen in the trained dataset, is misclassified, while soap from the United Kingdom is correctly classified. This is just one example of how underrepresentation can affect a model's ability to perform well on a dataset at deployment time. Other kinds of issues in the dataset can include images that are inappropriate or outright offensive and contain denigrating slurs. All of these are important things to know about a dataset because they could impact a model's ability to function in different contexts. With that being said, just as it is unclear whether biases in a pre-trained model will propagate into a fine-tuned one, the same goes for biases in a dataset. Thus, an understanding of the biases in a dataset remains a more exploratory early step that can help inform what might be important to look into for a trained model, but cannot guarantee whether a bias will or will not be presented in a trained model. There exists a number of tools that can help us to understand the context in a computer vision dataset. One such mechanism is the data sheet, which is a documentation that might accompany a dataset and describe things such as the collection process and recommended uses for the dataset. When using an existing dataset that has a data sheet, it's important to read and understand whether limitations of the dataset will have implications for the models trained on it. If creating a new dataset, it's important to create a data sheet to accompany it so that others know the contents and creation process of this dataset. In addition to this, it may also be useful to gain more understanding of the contents of the visual dataset itself. Two such tools that can help to do so include Google's Know Your Data, which analyzes TensorFlow image datasets, and a tool called Revise, which takes in any visual dataset and its annotations and outputs a set of analyses along the direction of object type, person attributes such as gender, race, and geography. Because image datasets these days are so large, on the order of magnitude of tens of thousands to even millions of images, these kinds of semi-automated tools can help to better understand the contents of the annotations and visual images in a dataset in a more tractable way. Returning to our example of filtering a large corpus of images for those with cars, we might want to consider the data set that the object recognition model we are using is trained on. Because we know that cars and roads may look different across geographic regions, we might decide that it's important to understand the geographic diversity of the training data set. Using a tool like Revise that we showed on the previous slide, we could get a sense of the geographic distribution of the training data set and see that most of the images are concentrated in America, Australia, and Western Europe. If we feel that the distribution of cars from countries outside of these regions is different enough, we may want to collect a more diverse data set to fine-tune our model on. Next, we will discuss the existing methods that can be leveraged to understand the biases in the model. We will consider interpretability in order to understand biases in the model's reasoning, and then evaluation to understand biases in the model's outputs. Within interpretability, there are a few different axes we can divide different methods into. One axis is between models that are interpretable by design and methods that are applied post hoc to a black box model. Interpretable by design means that models were explicitly trained to be interpretable. Another axis we could consider is that of explanations which are local or global. Local means that an explanation is for one specific image. For example, why one specific image of a cat was classified to be a cat. And global means that an explanation is for a model at large. For example, what a model considers to be cat-like features that cause it to classify something as a cat. There are different trade-offs to be made between all of these axes, and will determine which method is selected. For example, while interpretable by design methods are nice in that the model's reasoning process itself often serves as the interpretability, the cost is often worse performance. On the other hand, using post hoc interpretable methods may preserve the higher accuracy of a model, but interpretation methods may not be entirely faithful to how the model has actually reached its decision. Additionally, if you are trying to understand why a model classified one particular image as such, a method that provides a local explanation is more helpful. However, global methods can explain an entire output class for the model and can be more useful if the goal is to understand how a model works on all images rather than one specific one. There is a huge literature in the space of methods and models that span these axes. In this talk, we will just discuss two of them and how they may unveil fairness-related harms. This first method is called GradCam and is post hoc, so can be applied to an existing model that was not explicitly trained to be interpretable and is local, so provides an explanation for why a model classified a single image. It produces visual explanations from a large class of computer vision models by using the gradients in a model's classification to display the regions of an image that likely contributed to the classification of a particular label. For example, in the shown image of both a dog and a cat, GradCam on a model's classification produces what is called a saliency map. In the top saliency map, we can see that the model is looking at the top half of the image where the dog is for the dog classification, but then in the bottom saliency map, it is looking at the bottom half of the image for the cat classification. As an example of the fairness-related harms that interpretability can have, prior work has used GradCam to look at where an image captioning model is looking when it generates certain words. In this figure, the model is looking at a computer while saying a man, which is an example of a gender stereotype. GradCam helped us discover that not only was the prediction of the person's gender incorrect, but also the model's reasons were flawed. I'll note that this is a form of gender prediction, which should not necessarily be condoned. Next, we will discuss another post hoc method, but one that produces a global explanation, or in other words, explains how a model works at large in a way that is agnostic to one specific image. This method is called TCAV, or testing with concept activation vectors. It uses human-defined concepts, in this case, stripes, to understand how influential this concept is for the activation of a particular class, for example, zebra. It achieves this by using the directional derivative of the human-defined concept in order to gauge how sensitive the prediction of a particular class will be to any changes in this particular concept. Compared to the previous method, TCAV is able to give an explanation of how a model misclassifies all zebras rather than one specific image of a zebra. We can use this method to probe what a model has learned for certain class labels. For example, this shows that for the prediction of a ping pong ball, East Asian is a strong concept for certain models compared to other demographic groups. A model that relies on these kinds of spurious correlations can propagate undesirable stereotypes about groups of people. Once again, returning to our example of detecting cars for a social science research question, we may want to interpret a few things about how our model works. For example, we may believe that the color of a car is correlated with drivers of different demographic groups and want to understand whether our model relies on color when classifying a car. We may also wonder whether a model can detect cars that are imaged from a bird's eye view and thus do not visibly appear to have wheels. Because these questions are post hoc about a model that already exists and global rather than local, we can use a method like TCAV to answer them. Using TCAV, we can understand how the concepts of colors and wheels may influence car recognition. Finally, we need to evaluate the model to further understand the fairness implications of its outputs. The reason we need evaluation metrics is they can help us understand how a model performs for different groups and in different situations. As we saw before with the example of soap from Nepal, one kind of evaluation this can take is assessing the accuracy of a model, like object recognition, on images from different countries to ensure the performance is comparable. Importantly, evaluations of this sort require that there be labels indicating the demographics of the people in the image, or any other axis along which fairness wants to be measured. Different versions of accuracy parity across demographic groups are a common metric of fairness in computer vision, as discussed before. And a famous example of this is in the gender shades work, which found that the accuracy of a gender prediction model were significantly lower for people who are Black and female than people who are white and male. Another flavor of evaluation is in looking at the output distributions for images of different demographic groups. In one example of this, the research studies tags on similarly posed professional images of US Congress members and run it through Google Cloud Vision's image tagging system. They find differences in the outputs, such as that some of the top labels for men include official, business person, and spokesperson, while that of women includes smile, chin, and hairstyle. Yet another way of evaluating fairness is through a metric called bias amplification. Unlike other metrics, where some of the discovered bias is blamed solely on existing biases in the dataset, this metric captures additional biases amplified by the model on top of that which already exists in the dataset. For example, prior work has found that if cooking is 33% more likely to involve women than men at training time, a model may amplify this to be 68% at test time. However, in our later work, we point out serious assumptions made by the metric that are unlikely to hold in practice, such as that all demographic groups are equally represented in the dataset, and also only on binary attribute settings is it able to measure negative correlations. For example, that women don't appear with technology-oriented objects as much. In our work, we offered a new formulation of directional bias amplification that accounts for these shortcomings to capture when bias is amplified by a model. This highlights the need to carefully consider what our metrics are actually measuring and the normative assumptions hidden behind seemingly innocuous technical ways of formulating a metric. As is true in fairness work at large beyond computer vision, there's clearly no singular definition of bias that we can evaluate for, and a range of measures is needed. In the previous slide, we saw a large number of different ways to measure the biases in computer vision systems. However, we find that each operationalization of bias is somewhat different, and the different usages of the word are not always clearly articulated. A paper studying fairness work in natural language processing investigated this often underspecified notion of bias, which is not always clearly connected to an actual harm. Computer vision often suffers from the same lack of clarity as in NLP, where the term bias refers to a broad set of harms ranging from different performance metrics to specific stereotypes. This prior work has called for making clear what we mean by the word bias in each instance, and even making its connection to a harm more clear. In fact, even for disaggregated analyses, which may seem straightforward, there are careful considerations. For example, what performance metric is used for comparison, or on what dataset it will be evaluated on. To make these decisions, we need to look at where a model is situated. Prior work has argued that conceiving of fairness without thinking about the socio-technical frame it is situated in can make fairness evaluation and mitigation nonsensical. For example, trying to evaluate the fairness of a facial recognition system without understanding how that facial recognition system will be used in practice. Thus, we need to consider the entire socio-technical system, such as how this machine learning model will interact with people in the world. Zooming out a level, recent work has investigated measurement as a concept and how it plays into fairness evaluation. The construct of fairness itself is heavily contested, and without considering which theoretical understanding is most relevant for a particular task and the context it is situated in, any measurement approach is likely to have poor validity and reliability. Going back one last time to our example of card recognition for social science, one axis along which we might have fairness-related concerns is that of wealth, because people of different wealth tend to have different types of cars. Imagining a situation in which we had the prices of cars imaged in our dataset, we might decide that false negatives here are an important metric because if our model consistently misses cars that are worth less, this could lead to a persistent bias in the images filtered to the social scientist. So measuring the false negative rates of cars of different prices could be a worthwhile fairness evaluation in this setting. Even if we had the gender of the owners of each car, depending on the research question actually being asked, and whether people of different genders drive different cars, that might not even be relevant to look into. So in summary, in the first half of this tutorial, Seungbae covered an overview of biases in computer vision. He talked about understanding the origin and impacts of computer vision biases in media and society, and then reviewed types of dataset bias, model bias, and bias mitigation. In the second half of this tutorial, I discussed how someone might go about applying computer vision with fairness considerations in mind. Of course, the steps we discussed are not exhaustive, because fairness will always be an iterative and participatory process that incorporates the feedback of all relevant stakeholders. However, we did discuss how to get started, where it's important to first consider whether the task at hand is appropriate and look for available tools. Then, existing methods can be used to screen for biases in the data and models. Overall, we hope that this tutorial was able to introduce people to recent ideas in computer vision fairness and provide pointers to the literature. Thank you for listening.